Alrighty, folks, how we all doing? Happy Friday to y'all. Well, it's Friday for me. So you guys are not going to be watching this on Friday, but that's okay. So we're going to continue working our way through this idea of how derivatives apply to graphs and whatnot. So we've already talked about, we started off talking about the extreme value theorem, and then we went into a couple extra little theorems, Rolle's theorem and the mean value theorem. But we're going to get back to this idea of graphs, okay? So let's see if we can't draw a little bit here, and then we'll talk a little bit about it. So, now, extreme value theorem, when we're dealing with absolute extrema, which is the same thing as global extrema, it always required there to be some sort of closed interval. But we're going to be looking at more relative extrema today. Okay? So now relative extrema, and again, we've already kind of talked about this a little bit as well. Let's kind of throw them back out there. This right here, this would be a relative max. And this one right here, we'll call this a relative minimum. Now, these are located at kind of the extremes of our graph, when the graph's going up and down. What we care about today is we're going to spend time focusing on, first on these portions right here. The actual domains that lead up to it. So when we always pretend that we're going left to right, just like we did back in pre-calculus. So if we're going left to right here, we would say that this is an increasing domain. Now, if it's an increasing domain, that means that all the little tangent lines that go to it, so notice all these little tangent lines, even though they're getting more and more and more and more minimal as we go up, all these tangent lines would keep going like this. They're all have slopes that are increasing tangent lines. And if it's an increasing tangent line, all those slopes would be positive. Well, if slope is essentially related to the first derivative, again, remember, slope is average rate of change, instantaneous rate of change is derivative. It turns out on an increasing domain, all the derivative values are actually greater than 0 because it is increasing. Likewise, if we were to throw out the decreasing domain, we'd find out that they would all have derivatives that are less than 0. And likewise, if you notice here, I do have one more increasing domain, so let's just throw it out there. And maybe that might make a little bit more sense to us than about relative extrema, because we said relative extrema, those are always located at critical values. They're located at critical numbers. And remember what a critical number is. It's when a derivative is undefined or equal to 0. In this case, this particular relative maximum would be located on a line that would have a slope that would have a line which is equal to 0. Notice this one down here also has located a line where it would be equal to 0. And it kind of makes sense if you think of it in terms of the intermediate value theorem. If you're going from a negative number to a positive number number increasing, negative number decreasing, you'd have to pass 0, which is where that relative max is located. Same thing with relative min. If you're going from a negative value, decreasing domain, to a positive number, increasing domain, you'd have to somehow pass 0, which is a critical number where our relative minimum is located. So we can actually potentially write these in a little bit more, ground these in a little bit more of an idea. So a relative maximum, this is where the graph goes from an increasing domain to a decreasing domain. If we want to put it in terms of first derivative, it's where the graph It's where f prime of x changes from increasing, which is where our derivative is greater than 0, to decreasing, which is where our derivative is less than 0. And a relative minimum then would be really straightforward. Well, very similar to it. Relative minimum would go from, I can't spell today. That's what happens after you've done 6 Zoom sessions already in one day, from a decreasing domain to an increasing domain. Or it's where the first derivative changes from less than 0 to being greater than 0. So relative min and maxes, they don't exist just when a derivative equals 0 or it's undefined, because it doesn't have to change directions. The derivative doesn't have to change values as far as positive or negative goes. But relative max and relative min does exist when those things do happen, when it does go from increasing to decreasing, or decreasing to increasing. Or it does exist when your first derivative changes sign. And that's the idea that we're going to be playing with today. When it changes signs, that's when we are dealing with our relative min and maxes. And again, sometimes it doesn't change signs. So for instance, let's take a look at a point like this, just as an example. What if I had myself a derivative or a graph that goes here? Notice this derivative value right there, that's some derivative. It'd have a horizontal tangent line. So that C value would have it'd have a derivative value equal to 0. But notice, it's not a relative min, it's not a relative max, because the domain went from increasing, or a positive value, and it stayed positive. And this would be like a cubic function. It didn't change. It stayed going in a positive direction. All right, the derivative stayed positive. So just because a derivative is 0, it doesn't mean there's a relative maximum or a relative minimum there. Likewise, let's make that black again. Likewise, kind of got like a festive Christmas feel going here, don't we? Let's make another little dot here again. What if we had something? No, that's not a dot. There we go. What if we had something like this? Instead of a cubic function, what if we had like how about a cube root function? Cube root function has a point that looks kind of like where the derivative is equal to 0, but notice this looks like a derivative that is undefined because it has a vertical tangent line. All right. Critical numbers aren't just I'm running out of room here. I did it. All right, critical numbers aren't just when the derivative equals 0. It can also be when the derivative is undefined. Just like this one here is 0. Could be undefined. That's still a critical number. But just because it's a critical number doesn't mean that the graph, or it doesn't mean that there's a relative minimum or a relative maximum there. It has to change signs. The derivative has to change signs in order for there to be a relative extrema. By the way, if a graph never changes signs, ever changes signs, in other words, it's always increasing or always decreasing, that's actually a special type of graph. That type of graph is what we say that kind of graph is strictly monotonic. That's a type of graph that is increasing or decreasing for the entire domain. So sometimes a graph never, ever changes signs. And if that's the case, If it never ever changes signs, we'd say that graph is strictly monotonic. But relative extrema exists when the derivative changes signs. When the graph goes from increasing to decreasing, or decreasing to increasing, when the graph changes directions, that's when we have a relative extrema. And that's what we're playing with today. And we have a way to figure out where that exists, and that's called the first derivative. So I'm going to write out what the first derivative test is for y'all, and then we'll spend some time playing with it. First derivative test. It says a relative minimum exists at some point, C f of C, if f prime of x changes from less than 0 to greater than 0 at x equals c. A relative maximum exists at that point if the derivative changes from a positive derivative, in other words, an increasing domain, to a less than 0 at x equals c. Notice it's just, obviously they're the exact opposite. However, no relative extrema exists at c if f prime of x does not change signs at x equals c. So if it doesn't change signs, then there is no relative extrema. This right here, friends, this is a big idea. So we can locate where relative extrema are just by knowing what their signs are. Okay? And then, so that's going to be essentially what we play with today. How do we determine where the relative extrema exists for a given function? So here, let me give you an idea. So today is all about increasing and decreasing. Let's try that again. There we are. Whoop. Perfect. Determine all of the relative extrema for f of x of a given function. And that given function is going to be f of x equals 2x cubed minus 3x squared minus 12x plus 1. All right, so let's try this here. Determine all the relative extrema for the given function. So remember what we do. All right, get ready for the process. Remember what we do. We are always going to start off by saying what we're going to do. So we say what we're going to do. Then we do the work. When we're done, we're going to say what we found. So first up, relative extrema can exist or will exist when f prime of x changes signs. This can occur when f prime of x equals 0 or when f prime of x is undefined. So we start off, we say what we're going to do. And again, we said this is kind of like that idea. We're giving ourselves permission to go ahead and play with this idea of a derivative. So we say what we're going to do. Now, we sit back and we do the work. So I give myself permission to take a derivative. So I'm going to go ahead and take a derivative here. That's not the color I wanted. Yeah. So f prime of x equals 6x squared minus 6x minus 12. Now I've taken the derivative. Now I can set it equal to 0. I've got to figure out where those critical numbers are. So that way I can go ahead and determine if I have any relative extrema. So I factor. So that's going to end up being 6 times x minus 2x plus 1. So that means I have a critical number at 2 and a critical number at -1. Now, friends, that doesn't mean that those are going to always be where relative extrema are located. It just means that's where they can be located. I have to test it in my first derivative. So in other words, I know that my relative extrema, it could be at -1 and it could be at 2. So I'm going to essentially think of this as like at a number line, right? So -1 and 2. I have essentially, I'm thinking of it as like a number line. I have to test the intervals to see what my derivative values are. I'm going to test my derivative. So I'm testing my derivative here. So I'm going to pick some number, any number, doesn't matter, any number that is less than -1, say like -2. I'm going to pick a number between -1 and 2, like 0. Pick a number greater than 2, like 3. And I'm going to go through and determine, is this a negative derivative or would this end up being a positive derivative? If I plug this number in, will I get a negative value or a positive value? And when I plugged it in, I would have got a positive value. So that means that all the values there, all the derivatives on that side would have been a positive value. That tells me that my graph from -infinity to -1, that it's increasing. It tells me here, if I plug 0 in there, I'm going to get a derivative value, or any number between -1 and 2. I'd get a derivative value that is less than 0. It tells me in between -1 and 2, my graph is decreasing. And then from here, I'd find out that my graph goes back to increasing again because all my derivative values from 2 to positive infinity would be greater than 0. So that means, notice, I'm going from greater than 0 to less than 0. That means I have a relative max located when x equals -1. X equals 2, I went from less than 0, to greater than 0. That tells me when x equals 2, I had a relative min. My derivative changed from less than 0 to greater than 0. And again, remember, it has to change signs for there to be a relative extrema. So I know that I have a relative extrema at these values. So I need to go back and plug them in to figure out what values those are. So f of -1, I'm going to plug it in to figure out what that value is. It's the value of 8. When f is -1, when I plug it back in. So when we plug it back in, remember, we're going to plug it back into the original equation. Next up, I plug in my 2. If I plug 2 back into the original equation, I'm going to end up with -19. So I have a relative minimum at -19. So I said what I'm going to do. That was in purple. Then I do the work that was in green. And when I'm done, I'm going to say what I found. And remember, it's not just say what I found, but this time I have to explain it. Absolute extrema, the work explained it, but not for relative extrema. I have to explain it. So I have a relative maximum at the point -1, 8, because f prime of x changes from greater than 0 to less than 0 at x equals 1. -1, sorry. Relative minimum. So I'm saying what I have. but I'm doing a little bit more. I explain why. From less than 0 to greater than 0 at x equals 2. So let's take a look here. We started off by saying what we're going to do. And then from there, we did all the work. And when we're done, we say what we found. So we say what we're going to do, and then we do the work. And when we're done, we're going to say what we did or what we found, right? So we're going to just keep going through, and we're going to be doing the same idea over and over again, right? Well, let's have you guys try this yourselves. All right, so we're going to get rid of this first derivative test, and we're going to have you guys go ahead and try one of these yourselves. So boop, boop, there we are. I'll leave this here. Why don't you guys, first of all, we're going to do one more little thing to it. Determine when the given function, when f of x equals, let's see here, which function do I want to give you? Let's go with this. 3x to the 5th, and I'll have to go back and write that in a second, minus 20x cubed plus 2 is increasing and decreasing. Determine all of the relative extrema for f of x. So now, before you actually do the first derivative test, I'm going to have you actually tell me when is the graph increasing and decreasing. So I told you I was x to the 5th and 20x cubed. All right, friends, go ahead and pause the video. Let's see what you come up with. All right, you guys are probably just watching me use my magic eraser here now. I tell you what, now you've unpaused it, you've already solved the problem. So let's see here. Here we go. First of all, I'm going to say what I'm going to do. So I got to talk about increasing and decreasing here. F of x is increasing when f prime of x is greater than 0, and decreasing when f prime of x is less than 0. Okay, so I said what I'm going to do for that one. I'm also going to say what I'm doing here. Relative extrema can exist when f prime of x changes signs. I don't need to add to it as far as existing at critical numbers because I already talked about the derivative equal to 0. So this tells me for both parts, I'm going to be dealing with derivative, 0, and I can go ahead and deal with all of that from there. So I said what I'm going to do, and now I'm going to do the work. So derivative time, whoop, f of x, or f prime of x equals 15x to the 4th minus 60x squared. And I'm going to set it equal to 0. So I gave myself permission to do a derivative. I gave myself a permission to set it equal to 0 and solve it. So let's solve the dumb thing. We got 15x squared. And I have x squared minus 4. So we have x plus 2, x minus 2. So that means my critical numbers are 0, -2, and positive 2. So I'm going to go through and I'm going to check the intervals. What is the interval between each critical number? So what is the interval between -2 and 0 and positive 2? We're going to check them all. Can't really see the negative there, can you? Oopsies, didn't mean to do that. There you go. Now remember, when we go to check this, I'm looking for a number in every region, a number between -infinity and -2, one from -2 to 0, one from 0 to 2, and one from 2 to infinity. We're just picking a number. We just want to know what happens. That's it. Just want to know what happens. So I'm just picking random numbers that I'm going to plug into my derivative. Again, we're treating this like a number line. We're just picking numbers to test what happens in between my derivatives. So if I take -3 and I plug it in here, I would end up with a derivative that is going to be a positive value. If I plug -1 in, I'm going to end up with a derivative that is a negative value. If I plug +1 in there, hey, take a look. Still negative. It didn't change signs. That means there's no relative extrema. When I get there, there's no relative extrema at 0. There was nothing going on there. If I plug 3 in there, or 2 in there, 3 in there actually, it would change signs. So even though I had 3 critical numbers, I only had 2 relative extrema. I had a relative max because I went from positive to negative. Right here, I went from negative to negative, so I got nothing. Nothing happened there. And from here, I went from negative to positive, so that means I did have a relative min there. So I need to figure out those y values associated with them. So I need to plug in, and again, I'm going to plug it into the original equation now, not the derivative. I'm plugging it into the original equation to figure out what f of -2 is and f of 2 is. So I know where those relative extrema are. I don't care what f of 0 is. Nothing happened. No relative extrema there. Something happened. And we'll look into that later, but there's no relative extrema there. So -2, if I plug that in there, I'm going to get 66. I plug this in here, I get -62. So what are we going to write? We said what we're going to do. We did all the work, and when we're done, we're going to say what we found. F of x is increasing. When is it increasing? That's when it's positive. From -infinity. I'll have to go back and put the negative. I'll put the infinity symbols in here in a second. I don't have it on my computer. Sorry about that. To -2 and 2 to infinity, because f prime of x is greater than 0 from -infinity to -2 and from 2 to infinity. F of x is decreasing from, now some people will include 0. I personally like to separate them into 2 different ones, because at 0 was neither increasing or decreasing because we had a critical number that was equal to 0. But if you put -2 to 2, the College Board won't mark it wrong. I would, but College Board wouldn't. But because it's less than 0 from -2 to 0 and 0 to 2. So we have our increase and decrease. Now we can talk about our relative min and maxes. We have a relative maximum at, remember, relative maximums are, relative extrema are always written as points or locations, because f prime of x changes from greater than 0 to less than 0 at x equals -2. And we add a relative minimum as well. At 2, -62. Because f prime of x changes from being less than 0 to being greater than 0 at x equals 2. Let me go back and get those infinities in there because that's driving me crazy. Let's see here. Nope, wrong color. For math teachers, it sure would be good if we had like a key, just like a regular letter key for pi and for theta and for infinity. I'm telling you. All right. So again, you guys can probably already hear it in your head. We say what we're going to do. We do the work. And when we're done, we're going to say what we did, or say what we found. Let's try one more just to really make sure we kind of got it here, right? Let's try one more just to make sure we got it. So how about I give you something like this? I'm going to put it down here so you can see it while you actually do the next problem. Determine all of the relative extrema from on the domain 0 to 2 pi for f of x equals -2 sine x plus 1. All right, friends. Let's see what you guys can do with that. Go ahead and pause the video, and we'll talk about it here in a sec. All righty, here we go, here we go. Let's see what you guys came up with. So first thing we're gonna do, say what we're gonna do. We're gonna say what we're gonna do, and then we do the work. When we're done, we're gonna say what we found. Relative extrema can exist for f of x. Can exist when f will exist when f prime of x changes signs. This can occur when f prime of x equals 0 or when f prime of x is undefined. All right. So we gave ourselves permission to do our derivative. So that's exactly what we're going to do. We're going to do a derivative. So f prime of x equals the derivative of sine is cosine. So -2 times cosine of x. Derivative of 1 is 0. So we're gone. So we did our derivative. We set it equal to 0. And now we're going to solve it. So if I divide both sides by -2, I'm looking for when cosine of x equals 0. So when does cosine of x equal to 0? And again, you guys went through all your trig. Think of your unit circle. Cosine of x equals 0 when the x value is 0. That occurs at pi over 2 and 3 pi over 2. So that means x is pi over 2 and 3 pi over 2. Okay, so we got our values. Now we're going to go ahead and we're going to test them. Okay, so we're going to test it from 0 to pi over 2. Then pi over 2 to 3 pi over 2. So we're going to pick numbers in between there. Doesn't matter what numbers. If we wanted to, we actually could pick 0, even though it's between 0 and 2 pi. We could pick 0 there. So we got 0, we got pi, and I can go ahead and go 2 pi as well. It's fine, even though that's an endpoint. It'll still tell me what happens in there. So if I plug 0 into my derivative, I get cosine of 0 is 1 times negative 2 is a negative 2. That means in this region, my graph is less than 0. It has a derivative that's less than 0, not the graph, but the derivative. If I take pi and put it in, cosine of pi is negative 1. Negative 1 times negative 2 is a positive 2. So that means in here, I'm going to have a derivative that is greater than 0. If I plug 2 pi in there, well, 2 pi is the same thing as 0 because they are coterminal. So that's less than 0. And if we're looking at it, friends, here again, I went from less than to greater than. That means this is a relative min. And then from here, I went from greater than to less than. That means this is a relative max. So we're going to take our values and we are going to plug them in. So we're going to plug pi over 2 in. We're going to plug in 3 pi over 2. We're going to plug them back into the original equations, friends, original equations. And if I plug pi over 2 in there, sine of pi over 2 is 1 times negative 2 is negative 2 plus 1 is negative 1. That'd be a negative 1 right there, friends. Plug 3 pi over 2 in, sine of 3 pi over 2 is negative 1 times the negative 2 is 2 plus 1. That makes that 3. So we set what we're going to do. We did the work. So when we're done, we're going to say what we found, friends. And I won't be able to write the whole thing out because I'm going to have to come back and use my little drawing tool in a second. So we have a relative minimum at pi over 2, negative 1, because f prime of x changes from less than 0 to greater than 0 at x equals pi over 2. And then we have a relative maximum here at the point 3 pi over 2 comma 3 because f prime of x changes from f prime of x greater than 0 to f prime of x less than 0 at x equals 3 pi over 2. Let's go and write those in here. So we had pi over 2 here. That's the wrong color. There we go. And we had a 3 pi over 2 here. All right, and again, remember what we did here. We said what we're going to do, and then we did the work. And when we're done, we're going to say what we did. All right, friends. So there you go. That's the increasing, decreasing domains and the first derivative test. So kind of gives you a little idea where we're going with that. I'll see you tomorrow. We'll talk about maybe the second derivative.